so far I have really not worried about the fact that we have multiple dimensions in the input space, right. We just had this way of handling it, but then if you actually look at how statisticians typically present linear regression, okay, they will start off with a univariate regression. They will start off with one input variable and one output variable, right. So one independent variable and one dependent variable. So the independent variable is the input variable, right. So so whatever we have looked at so far is usually called multiple regression. People typically start off with univariate regression, people usually start off with univariate regression because it is easier to analyze. You can derive a lot of intuition into what exactly is happening with the regression, right. In fact, if you think about it, this picture I drew for you is with univariate regression with an intercept, right. So there is a column of ones and then there is one other variable, that is all, right. This is essentially univariate regression with a bias term, right. So these kinds, I mean, you can very easily develop all kinds of intuitions, and also analysis is very clean, and more importantly you can understand multivariate regression, okay, by a series of univariate regressions. So that is, we will look at it very quickly, and then we will see what happens. Right, so this is the basic model that we have, but here we are going to assume that x is a number, right. X is a single number, okay, so it is a single vector now, right. So my data will be of the form some x y, okay. So that is not a vector, it is just a simple x. So without the intercept. So why is it called the intercept? So the constant value you add is what the value of where it will cut the y axis, okay, so that is why it is intercept, okay. So I have no intercept, that means there is no beta naught here, okay. So now this one beta is given by right, essentially our original this guy for a univariate case. I am going to denote by Ri the residual error that I am making. So I made the prediction, right. So xi beta hat is the prediction I am making. So yi is the actual output I saw in the training data. So yi minus xi beta is the residual error, okay. And as before I am going to define okay. People I hope are familiar with the inner product notation of this form, which is essentially okay. Now can you tell me what beta hat should be in the inner product notation? Somebody said something, I heard a small squeak somewhere. Okay. Okay. So, this is fairly simple. So, one thing I will just point out in passing here, right, I am not going to cover it, you guys are happy to, I mean we are free to read up in Hasty, Tipshirani, Friedman's later chapters, which we will not get to, but the fact that I am using inner products here, okay, should tell you that I can apply the ideas of linear regression on any inner product space, okay, not just in real number space. Okay, so yeah, I will leave it at that. That gives you a good generalization. So, what we are doing here, I will call this as so we are regressing y on x, okay, and we get the coefficient beta hat. So, this is, remember what we are talking about so far is a univariate regression, right, no intercept, nothing. Okay. Suppose that your columns are all orthogonal, not only are they independent, they are all orthogonal. Okay. You can, little bit of thought, okay, you can convince yourself that each beta, so beta 1, beta 2, beta 3 and so on and so forth, are just given by regressing y on x1, x2, x3 and so on and so forth. So, beta 1 is regression of y on x1, beta 2 is regression of y on x2, right. Why is that the case? So, now my x1 and x2 are orthogonal, they are actually the orthogonal basis, an orthogonal basis for the p dimensional space, the p plus 1 dimensional space I am talking about, and each coefficient that I am going to get essentially would mean will be the intercept on each of the individual dimensions, the projection on each of the individual dimensions, because they are orthogonal in the lower space, right. So, that's easy to convince yourself. What is interesting is what happens if the x's are not orthogonal, they are independent, I mean, so they are still spanning a p plus 1 dimensional space, right, but they are not orthogonal. So, what do the coefficients represent in that case? So, that is essentially what we are going to look at. Okay, so, we will start off by taking one step at a time. Look at the intercept plus one variable. So far I said that is one variable without intercept. Okay, now I am adding the intercept. So what will be, what does that essentially mean for us? My x becomes 1 comma x, right. So here I had just a single value x, right, I could just write it like this. Now my vector x becomes so I am going to consider, right, so it is a column of ones and my original vector x, okay, this is my new vector that I am going to consider. Okay. So what I am going to do is, the first step I am going to do is sorry about that. Right. So this uppercase x is the actual column vector x consists of x. Okay. This is the actual input I am going to look at. Okay. Okay. So let me define x bar as the average of the all the inputs I have seen. Right, all the inputs I have received in my training data. Okay. So I regress x on 1, right, and form the residual. Okay. So what will the residual be?
Between the difference between the observed and experiment value.
Yeah, but in this case what it will be I am saying, because I am regressing on 1, all ones, right. So, if all ones is the only input variable I have, right, what should be the best possible prediction I can give? X bar, right. So, X bar is the only output I can give, that will be the one that minimizes the prediction error, right, because I am looking at squared error, the output should be X bar. So, my beta hat will be X bar in this case, right. So, the residual which I will denote by Z will be, okay. So, this 1 bar is just to indicate that it is a vector of ones, okay. So, this X is a vector. So, this X bar is a scalar value which is the average of all the inputs, and 1 bar is the vector of ones, so that this gives you the residual, okay. Does it make sense? Okay. So, this is the vector of residuals, okay. So, I usually put the bar on the X on the Z in the middle to differentiate it from 2, right, but sometimes it looks like lowercase z. So, is it fine? Let us adopt the convention that even if I put the bar there, it is still uppercase Z, okay, because otherwise I will have to be very careful about distinguishing 2 and Z and things like that. So, this is an uppercase Z, and if I really want you to look at lowercase z, I will write that, okay. So, the second thing I will do is now regress right. So, this is one univariate regression, okay, this is another univariate regression, okay. So, essentially this tells me, okay, I have taken the average value out of the input variables, because the average value can be used to predict the average output if I want. I have taken out the average value. So, whatever is left, okay, is the individual variations on the data point, okay, and use that to predict my output value y, okay. So, this essentially means that, so given that there are 2 dimensions 1 and x, okay, so the beta 1 hat tells me what is the contribution of x, okay, after I have used 1 to explain the output, okay. So, given I have taken care of 1 already, what is x. So, if you think about what I have done here, this is essentially making it orthogonal to the 1 vector, right. So, z vector is essentially the x vector, right, the component of x that is orthogonal to the 1 vector, okay, when going back to how we did the univariate regression, okay. That is what we have done here. So, does it remind you people of anything that you already looked at? Gram-Schmidt? People have come across Gram-Schmidt orthogonalization, right? It is essentially something very similar to that. So, I start off with 1 bar and x as the 2 vectors that span some space. Now, I am orthogonalized, I am just essentially giving you an orthogonal basis now. 1 is 1 vector and z is the other vector, but together they span the same space that was spanned originally by 1 and x, except that they are orthogonal. And people agreed with me earlier when I said that if the columns of x are orthogonal, then they can independently do regression on each of those columns. That is essentially what we are doing here. So, I have done a regression on this to get me beta 1, right. So, going back to our picture here, so essentially I had some x1, I had some x2, right. So what I did was I first regress x2 on this, so essentially I am getting, so that is my z, right, I am getting a orthogonal component to that. So now I have x1, I have z, and they are spanning the same, well, yeah, they are spanning the, okay, that does not look correct, right, geometrically. Okay, there you go, that is 90 degrees. So they are essentially spanning the same space. The z is a projection of x2. Imagine the plane is going into the board, right. So it does not look right to you, but the plane is going into the board. So z is actually perpendicular to x1, and it is formed by projecting, by regressing x2 on x1, okay, that is direction z. And my original y, which was going out of the plane, now I essentially project it on z to get the coefficient for, right, it does not matter, see this is still going to project here, okay. So earlier when I wanted the coefficient for x1 and x2, right, I would have looked at these points, right. Here now I will basically look at these points, okay, that is essentially what I have done. There is no change in the actual space, so the same y hat is what I will get, okay, but the coefficients I will be using for representing the y hat will be different. We can generalize this to p dimensions. So what will you get? Okay, let me finish up quickly. So J runs from 1 to p. So I will regress xj on all the previous z directions that I have determined, right. So how would I have determined z0? Well, z0 I start off with, z1 would have been obtained by regressing x1 on z0 and then finding the residual. So that gives me, so that is what we do here, right. So I take x bar, right, basically I have regressed x on 1 bar and then take the residual and make that as z. So likewise I will regress x1 on z0, take the residual and use that as z1, okay, then I will regress x2 on z0 and z1, okay, and then take the residual. So that is the gamma coefficient which we will, so in this case it was x bar, okay. So if you think about it, right, that will be x bar. So ZL, inner product with ZL when Z is all ones is n, right, and ZL inner product with x1 when Z is all ones is just x1. So this essentially will be with summation of x1, this will be just x bar, the first case, right, this is our gamma. Did it make sense or was it too quick? Yes, no? So I am saying this x bar was derived by just using the same formula, right. This happens when I regress on the first variable, right. So start off with z0 is 1, I am regressing x1 on z0. When I regress x1 on z0, what do I get? So Z naught, inner product Z naught is n, because just once, right, I have just sum up all the ones, so that is my dimension is n, that will be n, and Z naught inner product x1 will be summation x1, right. So summation x1 by n is essentially the average, right. So that is essentially what we had here, okay. So that is the same formula, and now I am generalizing to other dimensions. So I am still continuing the loop here, okay. So that loop that runs for j equal 1 to p. So for every j, and that is how I derive my zj, okay. So I take the current coordinate under consideration xj, okay, subtract all the previous dimensions I have basically looked at. So what I am left with, what am I left with? The orthogonal component of xj, okay, orthogonal with respect to the dimensions I have already looked at. So in some order I am considering it. So once I have done this for in some order, I am considering it in some order, right. When I come to the pth dimension, so what do I get? So what is beta hat p now? It is the actual coordinates, the actual coefficient that I will find for the pth variable if I had done the regression as we talked about earlier, right. If I had done estimated my beta like this, okay, this is essentially what I will end up with, okay. But because of the process we have generated it, we can interpret it in a slightly different way, which is essentially beta hat p tells you how much the pth variable contributes to the output, okay, given that we have adjusted for all the other input variables, okay, given that we have adjusted for all the other input variables, how much does the pth variable contribute to the output. Okay. Now we can go back and think about non-independent vectors. If any of the variables is not independent, right, so what will happen in this case? The residual will be 0, and essentially you will be trying to find how much would 0 contribute to the output, okay, okay, that is not going to be a lot, okay. But it becomes even more interesting if my vectors are nearly dependent but not exactly so. So what would happen is, if I subtract out everything else from that vector, right, so think of it like this, right, this is x1, that is x2, okay, this is the 2D plane, it is not like this, this is the plane, right. So x1 and x2 are very close to each other. So if I subtract out x1 from x2, okay, I am going to get a small component that is orthogonal to this, right, I am going to get something like this, right. Now if I take the inner product of that, so that will be a small number here, so this can become very large, right. So if my vectors are nearly dependent but not exactly so, so that the residual is not 0 exactly but close to 0, then the whole thing can become very unstable. Right? The whole estimation process can become unstable. So that is essentially what will happen even if you eliminate perfectly dependent columns, right, there could still be possibility of getting numerical instability. So to avoid all of these things, people have come up with various techniques that of course one of them is to essentially get rid of all the correlated or the nearly correlated columns, right, but then there are other ways of actually trying to get this to be stable. Okay. So just an aside, so let Z be the matrix that you create by taking Z1 to Zp as the columns. Okay. So I would have done this Z1 to Zp in this elimination process, right, in some order, right. So I will take this Z1 to Zp as the columns, okay, and gamma is the matrix where I store all my gamma hat kj. So it's a so it's an upper triangular matrix, right. So for every combination kj I will have one gamma hat value, I will just put it in the upper triangular part, and the lower triangular side I will just keep it as 0. So an upper triangular matrix there, right. And you can think about it, right, you can write x as z times gamma. X can be written as z times gamma, right. So essentially I am just stacking all of those things we have done together and we are writing it as z times gamma, right. And so D is a diagonal matrix where the diagonal entries are the norm of Zj, essentially inner product of Zj with itself, right. So the jth entry or the jth entry in the D matrix would be the inner product of Zj with itself, okay, that is the norm of Zj. So I can write it like this. So this is called the QR decomposition of X, right. So the thing about Q is it is orthogonal, right, Q is orthogonal and R is upper triangular, okay. So this kind of a representation for the data matrix, so this kind of a QR representation of the data matrix essentially gives you some kind of a orthonormal basis. Right, Q is not just orthogonal, it is orthonormal. Why? Because I am dividing by the norm here, okay. So the product will be ones or zeros because they are orthogonal to begin with anyway, okay. I have made them orthonormal. So Q gives me an orthonormal basis and R is an upper triangular matrix that lets me reconstruct the inputs X, okay. And this kind of a decomposition is very convenient and it is used widely in other kinds of representation or transformation of the data and so on and so forth.